Alright, so here we have a pretty nice problem from CENTRO 2018. This is problem 4, and it reads: determine all triples p, q, and r of positive integers where p and q are also primes, such that r squared minus 5q squared over p squared minus 1 is equal to 2. So my first instinct was to obviously, you can see this and you can convert this into p plus 1 times p minus 1, of course, difference of squares. But this, well, I mean, at least the official solution, it doesn't really go like that. In fact, we don't use the difference of squares at all. You see, the equation is rewritten. This is rewritten. So we have r squared minus 5q squared over p squared minus 1 equals 2. So you move the p squared minus 1 to the other side, and you also move negative 5q squared to the other side. The resultant r squared is equal to 2 p squared minus 2 plus 5q squared. And then we move the 2 to the other side, which results in r squared plus 2 being equal to 2p squared plus 5q squared. Right. So one interesting thing about this, firstly, is that back here in the original equation, we can move 2 down here, and to show that r squared minus 5q squared over 2 is equal to p squared minus 1, which just shows that r squared minus 5q squared is equal to 0 mod 2, which when we get to simplify, 5 is 1 mod 2, and we move this term to the other side, and this simplifies to r squared is equal to q squared, and then this is just r is equal to q mod 2. So what this implies is that r has the same parity as q. So r has the same parity as q. That's pretty important. Anyways, back to this, right? Basically, let's assume that p is not divisible by 3, and q is also not divisible by 3. So this is an assumption. Then neither p nor q are divisible by 3. Now, this means that p and q are either 1 or 2 mod 3. Then this means that p squared is equal to q squared is equal to 1 mod 3. So then this implies that r squared plus 2 is equal, since p squared and q squared are equal to 1 mod 3, then this would just be 2 times 1, and this would be 5 times 1. So this would equate to 5 plus 2, and this would simplify to r squared plus 2 is equal to 7, which is just 2 no, 7, which is 1 mod 3. So it'd be 1 mod 3. And then this means that r squared is equal to 2 mod 3. So it all simplifies to r squared being 2 mod 3. But this is a contradiction, right? Because any square that isn't a multiple of 3 is always going to give remainder 1 mod 3. Any number squared is going to be a remainder 1 mod 3 except, well, multiples of 3. So this is a contradiction. Thus, what this basically means is that 3 divides P or 3 divides Q. Furthermore, actually, P and Q are prime, so the only way that P and Q are divisible by 3 is if they're 3. So P and Q are prime, so P equals 3 and slash or Q equals 3. Okay, so let's do the first case. Let's do case 1. Let's say Q is equal to 3 and P is some other number. Then r squared plus 2 is going to be equal to 2p squared plus 45. And then this is going to simplify to r squared equals 2p squared plus 43. Now p isn't equal to 2. You can kind of see this because we can do a simple substitution. Else r squared is going to be equal to 51, and that's a contradiction. Thus, P will be odd because 2 is the only even prime number. Okay, well, little side note. The quadratic remainders of mod 8 are always going to be 1, 4, or 8. So the quadratic residuals or residues, to say it in in a more straightforward manner, any square will be either 1, 4, or 8 mod 8. Since P is odd, so this is like a little side note. Since P is odd, P squared will equal to 1 mod 8. Because if it's 4 mod 8, then it's going to be even, and if it's 8 or 0 mod 8, then it's going to be a multiple of 8, and that's going to be even. So P squared is going to be equal to 1 mod 8. So now we're going to switch it up and work mod 8. So P squared is going to be equal to 1 mod 8, and this is equal to 3 mod 8 because 8 times 5 is 40. So r squared is going to be equal to 2 plus 43. And that's going to be equal to 45, which is 5 mod 8. But as we just noted, r squared being equal to 5 mod 8 is a contradiction. Because any square will either be 1, 4, or 0 mod 8. So r squared being 5, that's not possible. So that means that this case does not work. Let's add additionally that p is not equal to 3. So yeah. Case 2. P equal to 3. And Q is not equal to 3. Then this is just going to imply that r squared plus 2 is going to be equal to 2 times 9 plus 5q squared r squared, and then that's going to just simplify to 16 plus 5q squared. And if you notice here, we can quickly check if q is even, aka if q is 2, and it's actually going to give us 16 plus 20, which is equal to 36. And that's actually 6 squared. That's 6 squared, which imply that r is equal to 6. So we would have a nice little pair here. I mean triple, which would be 3, 2, and 6. And let's plug that in just to make sure. So it would be 6 squared minus 5 times 2 to the 2 over 3 squared minus 1 being equal to 2, which simplifies to 36 minus 20 over 8, which is equal to 16 over 8, and that's equal to 2. So yeah, this is a pair. This works. Also, I just realized we don't, like, even if p is equal to 3 here, it's still not gonna hold, because if we say p is equal to 3, and then that means p is gonna be odd, and then that means that it's gonna lead to this contradiction even if p is equal to 3. So this is not gonna work. So if q is equal to 3 and p is any odd number or even number, it's gonna be a contradiction. The only case that works is if p is equal to 3 and q is not equal to 3, which gives us this. And let's quickly check if q can be any odd number. So let's call this 2.5. Then let's just do the same thing we did last time. Q squared is going to be equal to 1 mod 8. And then this is going to mean that r squared plus, no, whoopsies, my bad. R squared is going to be equal to 16 plus 5 times 1, which is just going to be, forgot to write mod 8 here, 16 is just 0 mod 8, so this is going to be equal to 5 mod 8, which is another contradiction. Therefore, the only pair, or triplet, sorry, that works is going to be, let me write it down, the only triplet that works is 3, 2, 6. And write QED in the corner. And we're done. Now this is a horrible, messy proof, but the point is there. It's kind of all over the place, but I'm not really used to writing digitally. Please give me a break. I'll get used to it. But yeah, that's pretty much it. It's an interesting problem. Gave me a lot of trouble when I was doing it for the first time. So yeah, I hope you understood. And if you have any doubts or any comments that you would like to tell me, any feedback, I would appreciate it. So yeah, thanks for watching, and I'll see you later. Bye bye.